In this video we're going to be talking about the tet mesh, which is this sort of lattice looking thing around the muscle geometry. The word tet in tet mesh is short for tetrahedron, and the tetrahedron is the simplest possible 3D primitive with volume. So if I was to draw it, it would look like that. And so our tet mesh is made up of multiple tetrahedra, and so each tetrahedron is an element of the tet mesh. So it's really a partitioned, or the technical term is discretized, representation of your geometry, which means there's a finite number of discrete elements representing this volume. So when we talk about the finite element method, that's borrowed from engineering. It's a useful tool for computing the physical behavior of solid materials. This is what we're talking about. We're computing the finite element method on our tet mesh. So all the physical forces and things get computed at that level, and then our original object is embedded within the tet mesh. So a cool thing about the way we construct our tet mesh is that it's decoupled from the original geometry object. So what that means is that we can adjust the resolution of the tet mesh completely non-destructively, which is a really powerful feature. It means that you can adjust the degrees of freedom without having to change any other parts of the system. So if you had attachments and things on here and fibers, which we'll talk about later, you don't have to change or delete any of that stuff. So one of the nodes that we get when we create a Ziva tissue object is this ztet node. And one of the attributes is tet size. So I could do, for instance, make this 50% of its original value. So do that. And you're going to see that now the tets are all uniformly smaller, and the resolution of the tet mesh is higher, which means there are more degrees of freedom when we come to simulate this tissue. Now the thing to remember is that the more elements you have in your system, the more tetrahedra, the more computationally expensive it is. So yes, you'll have higher degrees of freedom, you'll be able to get more rich deformation, wave propagation and things like that in your tissue objects, but your system's going to be slower. So it's about trying to find the right balance of the number of tetrahedra in your scene and the kind of physical performance you want to get out of your individual tissues. So for something like the jellyfint, which we have, which is that jiggly, cartoony elephant thing, which has a big fat belly, and you want to see the wave propagation going through all that material, you need to make sure that you have the right resolution in your tet mesh to support all that wave propagation and stuff. Another cool thing is that if you're really trying to optimize the number of tetrahedra in your scene, you can also adjust the resolution of the tet mesh across the surface of your original geometry. So many things in Ziva are actually paintable, and tet size is one of those things. So what we can do is set that back to what it was. And let's just say I want to have the tendinous areas at a higher resolution than the belly of the muscle. What I can do is right click on the mesh and then come down here to paint, and then under ztet I'm going to paint ztet weights, and I'm going to make sure this is painting white. And as I paint on this, you're going to see the resolution of the object change, of the tet mesh change, sorry. So that's a really powerful way of really optimizing the number of tets in your scene. So what's actually happening there is that map is multiplying against the surface refinement attribute on the ztet node. So you can think of this as kind of subdivisions in mesh smooth. So if I was to change this to 2, you'd see the resolution increase in those areas. Okay, so in the next couple of videos we're going to look at adding Ziva bone objects and how to attach tissues to bones. Alright, thanks for watching.